Is this realistic?
Boom. He flinched.
He flinched. So I want to say this is pretty realistic. He shoots, there's some kind of reaction, there's an explosion, blows out the door. And so now the gas is rushing out the door.
Mm-hmm.
And he gets flung by the gas forward. Gets pushed.
It pushes him. The gas behind him pushes him forward.
Yeah. And he moves relatively slowly. The gas is probably like whooshing by him, but because he's a high mass body, it like hits him and just pushes him slowly while most of it's whooshing around him, I think.
Okay, I like that. Yeah, like a wind tunnel. Yeah.
Yeah.
Ah, okay, yeah. And it's not just this one room. It's I think if I remember, Dawn says
open.
it's like the inner door is also open. So this is not just the gas from this room. This is like from the hallways and from the rest of the ship that's also getting pulled out, and it's pushing him forward with it.
Right, because I think if it was just this room, it would be like a instant gas is out.
Very quick. Yeah.
But we've asked to pull the gas from like a big volume of the ship, and it's got turned corners and whoosh around. It's going to take some time to get through to the outside, I think.
Right, and just like if you have a breeze coming from your windows through your room, if you close the door so that it's like barely open, you get the concentration of the wind, so that it's like really focused, really strong. Same thing here. You got a wind, you get air from the rest of the ship, but it's being focused down to that door, and so then it gets real high speed.
Yeah. Right, so that actually right there. At first I thought it was unrealistic because I was like, that's a steady stream of gas.
Can you point where you're looking at?
So I'm looking like right here.
Okay,
There's a steady stream of gas coming out the door. And I'm like, that's too much air. If it was just the room, it would be instant, just a blast of air, and that's it. But it's pulling air in from the interior of the ship, so that's going to take some time. So I think that is pretty cool.
Yeah, seems realistic.
Be at peace.
More evidence of like a flow from the interior of the ship that's taken some time.
Mm-hmm.
Be brave.
Dawn.
I pray I
Little
see
bitch.
you again.
Pulled out. Okay. He's pulled out. Yeah, didn't have the grip strength.
Yeah. Do some dead hangs, bro. Okay.
What are these these flecks here? What are these?
So I think that's water. And I think that's realistic in the sense of when you go, if you have water vapor in the air,
Okay.
and you go from atmospheric pressure-ish to zero pressure, which is the space,
Yeah.
then you're moving on the water phase diagram from a vapor to solid ice.
Okay.
And so when they lose pressure, the water wants to solidify.
So this phase diagram is like combinations of pressure, temperature, and the third one, which is
I think it's mostly just pressure and temperature.
pressure, temperature.
The standard phase diagram.
So depending on the combinations of the pressure and temperature, you could be in a different phase of water, so vapor, liquid, or solid. Okay. I remember high school chemistry teacher. They took water and put it inside a vacuum chamber and made it boil without adding any heat. So they sucked out the air pressure, which made the water like bubble up, boil, even though they weren't adding any temperature, any heat.
Right.
Okay.
Now, is the reason why it becomes ice crystal because the phase diagram makes it solid, or is it this evaporative thing where the evaporation pulls the heat away, which then crystallizes, pulls the heat away from the water, which then makes it solid? I can't remember. But I think it's realistic that you end up with crystals. Although I do think crystals are a little bit too large. If there's tiny droplets or water vapor in the air and there's a sudden decompression, then I think you get ice crystals, but they're going to be tiny. I don't think you're going to get these big chunky
snowflake, like small snowflakes, not these ice sheet flakies. Okay, but also I get it because like you can't show on screen tiny little crystals that are not visible. Like you got to make these things big.
Right. It might actually look like a cloud almost, like a fog.
Sure. Yeah.
Maybe.
Fog. I mean, I guess that is fog, right?
Mm-hmm.
Little water droplets in the air.
Yeah. So I think this is realistic, except they're a little bit too chunky, that there's going to be like particulates of water left behind.
Although
just floating.
Now that we're saying that, I'm surprised when we look at that left wall. So left wall and also the ceiling grates. It looks like those are frosted over, which I am surprised about. I'm surprised
Okay.
because what that means is that those sections are also cold, right? In order for
Okay.
the ice crystals to land and settle and not just melt,
Yep.
that wall and those grates must also be cold, which I don't think is right.
Okay.
I I don't think it's right because it's
Why
too
not?
fast. Exactly. I think it's too fast. Like you get all the air that
Okay.
gets sucked out,
Mhm.
and the room is already like, whatever many degrees Fahrenheit. It was already like a 77 Fahrenheit, 22 something, because people were in there. It's a room temperature. And so if you
Yep.
suck out all the air rapidly, I don't think you've had time for the room to cool. I think it's still roughly room temperature. I don't think ice would
Right.
have settled on it.
So what about like if you have a gas that expands, it cools
Uh-huh.
down.
That's
And
true.
the reason the gas when it expands it cools down is because it does work on the outside pressure, which reduces the internal energy of the gas as it expands,
Exactly.
which reduces the temperature.
I agree totally.
So is that an argument for this making that gas expanding out, cooling everything down?
So
And
okay, wait,
having
let's
deposition?
slow it down. So it's hard for me to imagine the cooling by expansion, but I can more easily understand the heating from compression. Or just
Okay.
like a piston. If you take a cylinder of gas and you like crush it real fast, just
Yep.
the act of crushing it real fast makes it get hot. I guess I guess the example of that is a diesel engine. Like you don't actually have a spark in there. Like you just have it crushes and then it gets hot enough the diesel goes off.
Yep.
So then the opposite of that, if squeezing something makes it hot, then expanding it makes it cool.
Yep.
And the way you said it in terms of physics terminology is the gas had to do work. It had to
Yep.
use energy to push the surrounding out. And so when it does work, it uses energy to expand its volume. Then its energy leaves the system, which the temperature is the average kinetic energy. So the temperature reduces. I don't think this applies here.
Okay.
For two reasons. One is because what is it pushing against? Like there's no like balloon or there's no like internal combustion engine cylinder. I think it's just free expansion into space. And so if there's no membrane, there's no wall, there's no balloon to push against, then the gas particles can just leave. Like they don't have to do any work. They don't have to spend any energy to expand.
Okay, I see what you're saying. So in the expansion case, you're always pushing against something to cool down the gas. But in this
Exactly.
case, it's pushing against space. Well, there's nothing in space. So there's
Exactly.
actually no pushing, which means no work. And because it's so fast, there's no heat.
Agreed.
So
Good point.
there's no work, no heat, no change in energy of the gas, which means no change in temperature.
Yep.
Which means if the grate is at room temperature and the gas is at room temperature, then they will end at room temperature.
I think
'cause there's
that's
no work
right.
done.
I think that's right. Although I'm not sure.
I know.
I'm not sure because the ideal gas law, which what we're talking about here, works at these. It's like it's quasi. What is it called?
Quasi equilibrium. Yeah.
Yeah, exactly.
Yeah.
So you can change states from different pressures, different temperatures, different volumes, but you have to do it real slow so that that the system is pretty much in equilibrium, quasi equilibrium. It is changing, but it's so slow that we can apply the equation at every step along the way. For these explosive stuff, I think the equation it may not apply at all.
Right. So we're pulling intuition from the ideal gas law and moving through a phase diagram or state diagram,
Yeah.
which requires this at every step of the way. We're pretty much in equilibrium.
Like a
But
slow
here it's this
change.
dynamic. Yeah, this is like a dynamic. We've got ballistic trajectories of gas particles. Things are not in equilibrium, so the ideal gas law intuition may not even apply.
May
In
not
fact,
even
I
apply
don't
at
think
all.
it does. In which case, will there be deposition of water on the grate? I still want to say no. That work argument is pretty compelling.
I think no. It's too fast. There's no time for that.
Yeah.
That whatever that wall is made out of, it's too fast for it to have cooled down.
Right, that's very fast cooling. Got to have fast cooling and then deposition as that happening as gas is rushing out.
Right.
That's
Exactly.
That's a lot. I want to say no,
I want to say no. But cool. Super cool scene.
but But this is
But I
good
don't
job
think so.
on the team. They've got a lot of this, I think, is correct.
I think
The
so.
amount of gas, the pushing, the rushing, the end state, which is like it's a vacuum with some crystals left over. Like pretty good, I gotta
Pretty
say.
good.
I think. Yeah.
Pretty good
Dawn.
folding of science reality into science fiction.
Yeah. Dawn though. Gotta work on your forearms, buddy.
Yeah.
Well,
Grip
I mean,
strength.
You're dead now, but
Could save your life. Get that bucket
right.
of sand. Dig.
yeah, let's dig. Yeah, do dead hangs, whatever you gotta do.
Get thick arms.
Yeah. And that's
That's
it.
our homework assignment for everyone. Get thick arms.